Welcome to section 1.6, Rules of Inference. We have talked a lot about rules of inference. Now we would look at rules of inference. Again, this is Dr. Gilbert Eyabi, and we are using the text Discrete Mathematics and its application by Kenneth H. Rosen's 7th edition. Section 1.6, Objectives. Number 1. We would look at valid arguments. When is an argument considered valid? Number 2, we would look at inference rules for propositional logic and how to use rules of inference to build arguments. Then we shall also look at rules of inference for quantified statements and building arguments for quantified statements. Let's go ahead and start. Let us start by revisiting the Socrates example. All men are mortal. That's a premise. Socrates is a man. That's a premise. How do we put these two premises together to come up with a conclusion? The conclusion was Socrates is mortal. How did we arrive at this conclusion? We would use rules of inference to arrive at the conclusion. So, an argument. When is an argument valid? We can express the premises from the example, Socrates is mortal, and the conclusion in predicate logic as follows. For every x, if x is a man, then x is mortal. Number 2, Socrates is a man. Therefore, the conclusion would be Socrates is mortal. So, the very first statement, all men are mortal, we translate that as for every x, if x is a man, then x is mortal. And the second statement, Socrates is a man, we translate that as Socrates is an example of a man. And putting those two together, we can come up with a conclusion that Socrates is mortal. We will show you further examples on how to put this together using what is known as rules of inference. Now, what is a valid argument? We will show how to construct valid arguments in two stages. First, for propositional logic, and then for predicate logic. The rules of inference are the building block, the essential building block in the construction of valid arguments, which means you need to know what the rules of inference are. Once you know what the rules of inference are, you can use those as essential building block in the construction of valid arguments. For propositional logic, we would use inference rules, and for predicate logic we would use inference rules for propositional logic plus some additional inference rules to handle variables and quantifiers. For every x there exists x, we would look at some additional inference rules that will permit us handle variables and quantifiers. So it's all about rightly applying rules of inference if we have to build or construct valid arguments. So let's go ahead and look at the first case, arguments in propositional logic. Here we do not have quantifiers and variables. So an argument in propositional logic is a sequence of propositions. All but the final proposition are called premises and the last is called the conclusion. So we have proposition 1, proposition 2, proposition 3, and the nth proposition we draw a line, therefore Q. P1 to Pn are called premises and Q is called the conclusion. For it to be valid, the premises must all lead to the conclusion and it has to follow rules of inference. In other words, if P1 is true and P2 is true and P3 is true and Pn is true, therefore Q has to be true. And that only happens if the rules of inference are not violated. If they hold. The argument is valid if the premises imply the conclusion. An argument form is an argument that is valid no matter what propositions are submitted into its propositional variables. So if the premises P1, P2 up to Pn and the conclusion is Q, then what we are saying is P1 and P2 and Pn implies Q is a tautology. Okay? Inference rules are all simple argument forms that will be used to construct more complex argument forms. In other words, inference rules will be used to show that more complex arguments are valid. So let's go ahead and look at the rules of inference. There are a couple of them. I do not expect you to memorize the various names of the rules of inference, but I expect you to master the rules of inference, even if you know the names or not. The very first one is known as modus ponens. That is the most common rule of inference. And the rule says if P implies Q is true and P is true, then I can conclude that Q is true. That is modus ponens. If it is sunny, I will go out and play soccer. It is sunny. What is expected of me? I have to go out and play soccer. More examples. Let P be it is snowing and Q be I will study discrete math. If P implies Q is true and P is true, then what is the obvious conclusion? Q has to be true. If it is snowing, then I will study discrete mathematics. That is the statement you've made. It is snowing. Therefore, what is the conclusion? I will study discrete mathematics. Easy and straightforward. P implies Q is given. You stand on that implication. P is true. Therefore, I can conclude that Q is true. And you can verify that P and P implies Q. All of this, that is the first proposition, and the second proposition implies Q is a tautology. Okay? The second rule of inference is known as modus tollens, which actually is modus ponens contrapositive. The contrapositive of modus ponens. If P implies Q is true, i.e. that is the statement we have made, and not Q is true, what is the conclusion? The conclusion is not P. To easily see this, remember that P implies Q. The contrapositive is not Q implies not P. So I can rewrite P implies Q as not Q implies not P, and then not Q. By modus ponens, my answer would be not P. Okay, so you see that modus tollens is just the contrapositive of modus ponens. Example, P is it is snowing, and Q is I will study discrete math. So what is P implies Q? If it is snowing, then I will study discrete math. What is not Q? I will not study discrete math. What is the obvious conclusion? It is not snowing. Okay? So that is modus tollens. Again, I do not expect you to remember the names, but you have to remember the rules of inference, because that is the only way you can build valid arguments, or is the only way you can use to verify that a given argument is valid. The next one is hypothetical syllogism, which I probably would just call transitivity. P implies Q is true. Q implies R is true. Therefore, the conclusion is P implies R. And you can show that this would form a tautology. So the easiest way to look at it would be if P implies Q is okay, Q implies R is okay, then I can conclude that P implies R. That's hypothetical syllogism. P is it snows, Q I will study discrete math, and R I will get an A. If it snows, then I will study discrete mathematics, if that is true. And the next statement is, or the next premise, if I study discrete mathematics, I will get an A. What is the obvious conclusion? If it snows, I will get an A. Okay? We would give you a bunch of premises and ask you to use that bunch to come up with a valid argument, a valid conclusion. And you would need the rules of inference to come up with that. And transitivity is actually going to be the most popular way of thinking to come up with a conclusion, given several premises. And the next one is disjunctive syllogism. Again, to me, it's just a very big word which you really don't have to worry much about. All you need to think about is, if I have P or Q to be true, and one of them is false, then it has to be the other one. That's easy. P or Q is true. I would either take a slice of pie or a scoop of ice cream. I tell you that very clearly. For dinner today, I will take a slice of pie or a scoop of ice cream. And you are told that I did not take a slice of pie. What is the obvious conclusion? I took a scoop of ice cream. Okay. So that is disjunctive syllogism. If P or Q is true and P is not true, then I can conclude that Q has to be true. Another example. Let P be the statement, I will study discrete math. That's a premise. And Q the premise, I will study English literature. Now, I give you this statement, and it's a true statement because that is what is in my heart. I will study discrete math or I will study English literature. So that is why I tell you before going to the library, I will study discrete math or I will study English literature. So that is true. I put that out there. When I get back from the library, you say, how did it go? I tell you, I did not study discrete math. What is the conclusion? I studied English literature. Okay, so that's very easy. And the next is addition. Addition is also very simple. If I add a slice of pie, that means I add a slice of pie or a scoop of ice cream or a plate of salad or whatever it is. I can add anything to P as long as P has already been performed. Anything can be added to P using the connective or. Remember, or is inclusive or. I cannot use the connective and. On the other hand, if I have P and Q, then it means P has been done and Q has been done. Any one of those would be a valid conclusion. I ate a slice of pie and I took a scoop of ice cream. What's the conclusion? I ate a slice of pie. What's the conclusion? I took a scoop of ice cream. You see how and or play around. So addition, if P is true, then I can always conclude that P or Q is true. So P is I will study discrete math and Q is I will visit Las Vegas. So if I know that I will study discrete math for sure this summer, then you can conclude that this summer Dr. Eyabi will study discrete math or he will visit Las Vegas or he will go down to Cameroon or he will go up to Boston. You can add as many things as you want to add using or. And that rule of inference is known as addition. Okay. What about simplification? That's what I just mentioned. If I know that P and Q is true, then I can conclude Q or I can conclude P. Either of those would work. If P is I will study discrete mathematics and Q is I will study English literature, and I tell you I will definitely study mathematics and I also will study English literature, and somebody comes by and says, hey, what's Dr. Eyabi going to study? He's going to study discrete math. You are correct. Another person says he's going to study English literature. You are correct. That's because I'm going to study math and English literature. So that rule is known as simplification. The next is known as conjunction, and that is very straightforward. If P is true, Q is true, then P and Q is true. P is I will study discrete math. Q is I will study English literature. If I studied discrete math, if I studied English literature, then I did study discrete math and English literature. Very straightforward. And the next is a resolution. This is one of the things that would make a logician or a mathematician in general to be a very good lawyer. You can come up with some very good resolutions in court. If I do know that not P or R is true, and I also do know that P or Q is true, then what is the obvious conclusion that could be drawn from these two premises? Q or R is true. That rule of inference is known as resolution. Example, P is I will study discrete math, R is I will study English literature, and Q is I will study databases. So I tell you, I will not study discrete math or I will study English literature. I will study discrete math or I will study databases. You leave my presence, what is in your head for sure? He is going to study English literature or databases. Remember, this two is linked up with and. I.e., if I do know that not P or R is true and P or Q is true, then my obvious conclusion is Q or R. Okay. Using the rules of inference to build valid arguments. A valid argument, as we've mentioned before, is a sequence of statements. Each statement is either a premise or follows from the previous statements by rules of inference. The last statement is called a conclusion. So a value argument takes the following form: S1, S2 up to Sn, therefore the conclusion C. Now, in this class, I would not really expect you to write down your statement in the form S1, S2 up to Sn, as long as you can come up with a valid argument without necessarily listing out all the names of the different rules of inference you've used, but you've obviously used them. That should be good enough for me. For example, from the single proposition P and P implies Q, show that Q is the conclusion. So use this and show that the conclusion is going to be Q. So we have P is true, P implies Q is true, show that the conclusion would have to be Q. Now, if you break this down in the form of premise and then conclusion, we have P implies Q, and simply means underneath that I have Q. That means underneath that I have P, so that becomes modus ponens. This is true. By modus ponens, my conclusion is going to be Q, and that is perfect. And I could use truth tables to show that that gives me a tautology. Now, if we want to use the concept of valid arguments as described by Kenneth H. Rosen, this is what we would see. So P and P implies Q is a premise. So by simplification, P and P implies Q. I could take either this or that. So I decide to take P, and also I take P implies Q. So I end up with P and P implies Q, and all of this is by simplification. And using 2 and 3 by modus ponens, I get Q. I would be more than okay if you just said, because it's an and, that means the first two premises stay on top of each other, and then a line is drawn, and then tell me by modus ponens the result is Q. That's good enough. If you cannot remember that is called simplification, that's okay. Valid arguments, example 2. I particularly like this example because you would see some questions from the author, Lewis Carroll of Alice in Wonderland, that would expect you to put a couple of premises together and then come up with a conclusion, the best conclusion. And that will be the conclusion that uses all the premises given. And you do that using rules of inference. And the favorite rule of inference that you would use would actually be transitivity. Remember the very complex name? But let's just stick with transitivity. Let's see how that is used here. The first premise is this: it is not sunny this afternoon, and it is colder than yesterday. 2. We will go swimming only if it is sunny. 3. If we do not go swimming, then we will take a canoe trip. 4. If we take a canoe trip, then we will be home by sunset. Question: come up with a conclusion that uses all the premises given. In this particular example, you are actually giving the conclusion, but let's say the conclusion was not given. I give you these 4 premises and ask you to come up with the best conclusion, which is one that uses all the premises. So, this is what we do. Let P be, it is sunny this afternoon. R, we will go swimming. T, we will be home by sunset. Q, it is colder than yesterday. S, we will take a canoe trip. Now, let me show you my translation. Number 1, it is not sunny this afternoon and it is colder than yesterday. I translate that as not P and Q. It is not sunny this afternoon. Q, it is colder than yesterday. So that's my translation. I go to statement number 2. We will go swimming only if it is sunny. I try to write that in the form if then. If you go back to the equivalent ways of writing if then, this is simply if we go swimming, then it is sunny. So that becomes if we go swimming, then it is sunny. So that becomes R implies P. Now watch very carefully what I do here. I immediately write the contrapositive of R implies P because both are equivalent. The contrapositive of R implies P is not P implies not R. Take a deep breath. The second premise is written. Now let's move on to the third premise. If we do not go swimming, then we will take a canoe trip. If we do not go swimming, not R, then we will take a canoe trip, and that is S. So my next premise is not R implies S. I immediately write the contrapositive of that premise, which is not S implies R. Remember, the contrapositive of P implies Q is not Q implies not P, and not P is just P. Deep breath. Premise number 3 is done. Premise number 4. If we take a canoe trip, then we will be home by sunset. If we take a canoe trip, S, then we will be home by sunset implies T. So my fourth premise would be S implies T, and the contrapositive is not T implies not S. You take a deep breath, we have all 4 written, and there are various contrapositives. Now, how do we link up all 4? All 4 must be linked up using transitivity. Wait a minute. It looks like not P and Q would imply not P. That is simplification. I have used number 1, the first premise. 3 more premises to go. So simplification gives me that. Then, wait a minute. I see here that not P implies not R. That is premise 2. And I stay right there. And I see not R implies S. That's premise 3. You see, I am using either the original proposition or its contrapositive to create my chain. So not R implies S, and then I use 4, and I have S implies T. So what is my conclusion? My conclusion would be where I start ends up with T. So what is the obvious conclusion? Or what is the one statement which I'm trying to reveal using all 4 propositions? If it is not sunny this afternoon and it is colder than yesterday, then we will be home by sunset. In other words, the conclusion is T. We will be home by sunset, provided we start off with it not being sunny and it's colder than yesterday. So all the other things in the middle, the canoe, the swimming, and so on and so forth, they've all disappeared. I'm left only with the first and the last. If it is not sunny and if it is colder than yesterday, then we will be home by sunset. That gets really exciting. So if you want to tell your friend something, but you don't want to make it really easy for that friend, you can decide to talk to the friend in 10 different premises and leave it there. And let the friend put the 10 premises together and come up with a conclusion, which is exactly what you're trying to say. Go ahead and try that. Maybe start with 3 premises or 4 or 5 or even 2 and see if your friend can figure out what you're really trying to say using all those different premises. Math is beautiful. Okay, of course, using the method by Kenneth H. Rosen, you have all these beautiful things written, simplification, modus tollens, and so on and so forth. But our conclusion would always be T. Quantified statements. How do we handle quantified statements? Valid arguments for quantified statements are a sequence of statements. Each statement is either a premise or follows from previous statements by rules of inference, which include number 1, rules of inference for propositional logic, and number 2, some additional rules of inference for quantified statements. So the rules of inference for quantified statements will be introduced in the next couple of slides. Let's go ahead and look at those. The first one is known as universal instantiation, UI. Wow. Such a beautiful word. But what it actually means is, if P of X is true for every X, then P of C is true, where C is a particular case. And that is pretty obvious. For every X, where X comes from the domain, which is the set of students in your class, for every X, X likes discrete math. Peter is in your class. What does that mean about Peter? Peter likes discrete math, period. Okay, so don't bother much about UI or universal instantiation. What I need you to remember, because we shall use this in proofs, if you are given for every X P of X, that means P of C is going to be true for any particular C. All dogs are cuddly. Fido is a dog. What's the conclusion? Fido is cuddly. All men are mortal. Socrates is a man. So Socrates is mortal. All the students at Anderson University are hospitable. John is a student at Anderson University. So John is, good job, hospitable. The next is universal generalization, UG. And this is actually almost the same as universal instantiation. And we actually do use that a lot in proofs. If P of C is true for an arbitrary C, then I can conclude that for every X, P of X is true. If I pick any C, P of C is true. I pick any C, P of C is true. I pick any C, P of C is true, of course, from the domain that I'm interested in. Then I can conclude that P of X is true for every X in the domain. That is known as universal generalization, UG. And again, as I mentioned before, we shall use this implicitly in mathematical proofs. We shall see that in sections 1.7 and 1.8. What about existential instantiation? Wow, that's another big word. But that simply means if I am told that there exists X such that P of X is true, that means there is at least one person in that set C such that P of C is true. So there exists X, P of X. If that is true, then P of C must be true for some element C. There is a particular example for which P of X is true and call that example C. There is an honest faculty at Anderson University. Then I know that by the time I run through all the faculty at AU, there's going to be a faculty C that is honest. That is called existential instantiation, EI. There is someone who got an A in the course. Let's call her A and say that A got an A. That was a good one. Next, existential generalization, e.g. P of C is true for some element C. Then I can conclude that there exists X in the domain such that P of X is true. So if it is true for one particular C, then there exists X, P of X is true in the domain. There is an element such that P of X is true. For example, Michelle got an A in the class, so I can conclude that there exists a student X in this class such that the student got an A. Okay, so how do we use rules of inference? Example, using the rules of inference, let's construct a valid argument to show that John Smith, J, has two legs is a consequence of the premises. Number one, every man has two legs. Number two, John Smith is a man. Every man has two legs would be for every X. M of X implies L of X. This is implies right here. M of X would mean the person is a man, and L of X would mean the person has two legs. And then we have M. John Smith. John Smith is a man. Then by UI, universal instantiation, which you do not really have to memorize, you can conclude that L. John Smith. John Smith has two legs. And you can put the premises down as follows. For every X, MX implies L of X. So, a particular case, MJ would imply LJ. MJ is true, therefore by modus ponens, LJ has to be true. Number two, using rules of inference. Let's use the rules of inference to construct a valid argument that shows that the conclusion, someone who passed the first exam has not read the book, follows from the following premises. Number one, a student in this class has not read the book. Two, everyone in this class passed the first exam. Okay, so if CX is X is in this class, BX is X has read the book, and PX is X passed the first exam, then we can translate the following premises as follows. Number one, there exists a student X such that, remember, such that C of X and not B of X. The student is in this class and the student did not read the book. And for every X, C of X implies P of X. If the student is in this class, then the student passed the first exam. And if I put these together, what is my obvious conclusion? There exists X such that P of X and not B of X. The student passed the first exam and the student did not read the book. Very straightforward. You do not have to tell me whether you use disjunctive syllogism, hypothetical syllogism, and so on and so forth. Just straightforward argument. Now, using the approach by Kenneth H. Rosen, these are the premises. The general case, particular case, general case, particular case. Put all the particular cases together and then come up with the conclusion. Okay, so if we go back to our Socrates example, it's very obvious. For every X, if X is a man, then X is mortal. Socrates is a man, therefore By universal instantiation, we can conclude that Socrates is mortal, which of course, if you break that down into arguments like Kenneth H. Rosen would do, you go from general to particular and then you apply modus ponens, you still come up with the same conclusion: Socrates is mortal. Right here, for every x, if x is a man, then x is mortal. By universal instantiation, we can do man Socrates implies man mortal, reduce that to a particular case, and we also have Socrates is a man. Then we can use modus ponens and conclude that Socrates is mortal. Now, instead of talking about universal instantiation, then we go back to modus ponens and so on and so forth. There is something known as universal modus ponens. Universal modus ponens combines universal instantiation and modus ponens into one rule. For every x, P of x implies Q of x, and P of A is true where A is a particular element in the domain, then my conclusion is Q of A. Universal modus ponens. So modus ponens is so important that instead of going through universal instantiation, get a particular case, then apply modus ponens, we simply talk of universal modus ponens, and that puts both together. If I know that for every x, P of x implies Q of x, and that P of A is true for some particular A in the domain, then I can conclude with all confidence that Q of A has to be true. And that is the rule we use in the Socrates example. This brings us to the end of section 1.6, Rules of Inference, and sets the stage for us to start dealing with proofs. Proofs would be very important in this class, and you're going to use the concept learned from sections 1.7 and 1.8 in further classes in mathematics: abstract algebra, advanced calculus 2, abstract algebra 2, and many other proof-oriented classes here at Anderson University, including linear algebra. We look forward to a beautiful time dealing with proofs. Thank you, and God bless you.